from what you've seen before. It's a different way of learning. But I think there's a sort of interesting duality. So what we're going to do is we'll do a quick review of what we talked about in, I think, lecture 1, overdetermined systems. And then map that onto underdetermined systems. And then we'll introduce Bayesian regression, particular with univariate Bayesian regression. And then we'll briefly look at the multivariate case. But we'll do more on that in the lab. So remember in week 1, something's gone wrong with my colors here, but with a system of 2 simultaneous equations with 2 unknowns, we could fit a straight line. And that was straightforward to do. But the additional observation leads to an overdetermined system. So what we've been looking at is ways of dealing with that. In particular, we introduced a noise model. And the noise model said, okay, well, what we observe isn't really directly from the system. It's coming from a corruption of the system. So we sample a sort of epsilon, which is the corruption, and add it to our existing model. And actually, we add all these different variables. But then we have this distribution over these variables. So that was how we dealt with an overdetermined system. And this noise model is giving us the mismatch between what we're modeling and what we expect to see in the data. I always think of a noise model. It has various, what people think of as noise can vary from field to field. So I think for machine learning, the best way I like to think of it is it's the mismatch between the way I'm trying to model the data and what I'm actually seeing in the data. That's the noise. You can justify a Gaussian noise by appealing to central limit theorem, but other noise models are possible. So we're not going to look at student T, but it's not always the case that noise is Gaussian. Sometimes it can be heavy-tailed. So you can get sort of a heavy-tailed noise is one where you might have an occasional corruption that's very large. So normally you have small corruptions, but then every 1 in 100 you have a really, really large corruption. And that would be a heavy-tailed noise. And if you're going to use that, you have to look at other distributions for the noise, things like student T distribution. But if you use the Gaussian density, and this is what Gauss pointed out, and you use Gaussian noise, this leads to least squares. And we saw the sort of text for that in the last lab. So this is, again, our world model. But what happens in the case where, OK, that was the 3 observations. Oh, that's all Laplace stuff. Oh, I don't know why that's in there. Get rid of that. OK, what about this case? What if you've got 2 unknowns and 1 observation? So now this is what we're going to model. I think this is the interesting place to be modeling, actually, personally. Often you're not modeling in this case. You may have much more data than you have. But for me, this is the interesting domain. So you've got 1 observation, and your model is that you're going to fit a straight line to that observation. So what could we do in this case? First of all, the previous system was known as an overdetermined system. Does anyone know what you'd call this type of system? Underdetermined, yeah. Very good. It says at the top. So this is underdetermined because we only have 1 observation. We've got 2 unknowns. So with our 1 observation, we can't determine both of these unknowns, right? So what are we going to do? Let's have some suggestions for how we could deal with this. What might I do? Randomly add another observation. That's a very interesting idea, actually. And in fact, what we'll end up doing could be interpreted as being similar to that. So yeah, that's something you could randomly add another observation somewhere along the axis, put it in, and then you could fit the line. So that's something you could do. We're not going to do that. Whether it's valid to do that, and these are the sort of questions, is it valid to do that? Well, you know, potentially, actually, I think it could be. I think that relates closely to something that we're not going to study, but called the bootstrap. What else could we do? What did we do before when we had the overdetermined system? The first thing we did was we added epsilon into the system. Yeah? So we had a new epsilon in the system. And then what did we do with epsilon? How do we treat epsilon? So adding epsilon into the system did something. Because if you look at the set of equations that we had before, turns out that when you look at it, this system now has 1, 2, 3, 4, 5 variables, right? Instead of just the 2 variables that it had before. And it's got 3 measurements. So this system, by adding epsilon in, what does it turn the overdetermined system into? An underdetermined system. So our way of dealing with an overdetermined system was actually to turn it into an underdetermined system, because we added 3 extra parameters or variables. Does that make sense? But then what do we do with epsilon? How do we get rid of epsilon? What do we use to get rid of epsilon? What do we assume about epsilon that I just talked about 20 seconds ago? Pardon? We assumed it came from a Gaussian distribution. So we introduced additional variables, and then we put a probability distribution over the additional variables. Okay. So what about this situation? What could we do here? So first of all, for example, I can motivate this by saying, well, we could actually, if we knew C, we can compute M. So your sort of comment earlier was, well, what if we assume a random distribution for an additional data point? Well, what if we assume a random distribution for C? What if we make an assumption about what C is? So let's assume C is 1.75. This gives us a value for M of 1.25. But the problem with this is, how are we justified in assuming C is 1.75? Where did we get that from? You know, I've just sort of sampled that from a distribution. I shouldn't just stick with that. I should consider more possibilities for C. So I could assume a second example. So this time C is minus 0.077, and that gives us an M of 3.78. In fact, I can consider a family of C's. So here, I've sampled C from a Gaussian density with 0 mean and variance 4, so standard deviation 2. So we get occasional ones up round 4. And then I've just computed the resulting M, given the C, and I've given a plot. Now, I think that's a pretty reasonable thing to do in this case. No, we're not assuming any noise, so everything's going through the point observation. But what we're saying is that there's a family of possible solutions that could fit. And we're actually doing the same thing. This is, I haven't seen anyone else really point this out apart from me, but it was presumably thought about like that. But you're also doing the same thing with noise. When you look at what you're doing with noise, you're first introducing additional variables, and then you're assuming a family of solutions for what those variables are, drawing from a Gaussian. People don't tend to think of that as a Bayesian approach, and we'll come on to why that is considered philosophically distinct in a moment. I really don't like the term Bayesian. It makes it sound like a cult or a religion. It's not. But what people mean by when they say Bayesian is assuming prior probability distributions for the parameters. Dealing with this underdetermined system, you don't have to have an underdetermined system to do this. You can do this with an overdetermined system. But making an assumption that the parameters are distributed according to some distribution. So here we've assumed Gaussian. So I don't really recognize personally this distinction. I think this distinction is a false dichotomy. But it is there, and you can see some reasons why people have this. What people say is that the first type of uncertainty we're assuming is aleatoric uncertainty. So the type of uncertainty where it's sort of noise, and we're putting a prior distribution over that, is known as aleatoric. The second type of uncertainty is known as epistemic uncertainty. And there's a difference between these two for our purposes is as follows. So I like watching sport, but I don't really have time to watch sport, and I often don't have time to watch sport when it's on. So one of the things I'll often do, which is becoming increasingly difficult to do, is I'll not watch the match on TV when it comes on, but I might wait and watch highlights or a recording of the match later. Now, it's just as exciting to watch the recording of the match if you don't know the result. as it is to watch the live match, right? It doesn't really make a difference. It spoils it a bit if you know the result. If someone comes in and say, oh, did you catch the match? England lost, they're out of the World Cup. You know, then you're like, oh, okay, well, pointless watching the rest of this then. And then you go into the garden or something. But there's a distinction between these two types. People would recognize, they would say that the uncertainty about the result of a football match or a rugby match or a Formula One race or any series of events like this is aleatoric uncertainty. It's natural underlying stochasticity. Whereas epistemic uncertainty is the sort of uncertainty, the idea is it's something that could, in principle, be known. Like, if the match has already been played, you could just look up the result. Your uncertainty about it is not because there's any underlying stochasticity. There is a known result that you could observe. Does that make sense? So when you're watching the match recorded and enjoying it with the uncertainty, you're enjoying epistemic uncertainty. When you watch the match live, you're enjoying aleatoric uncertainty. Now, epistemic and aleatoric, so for example, does anyone here know what color socks I'm wearing? Black. Yeah, I mean, you can make guesses, can't you? Any other guesses? Pardon? Navy color. Yep, these are good guesses. So what type of uncertainty are you expressing when you're coming up with these different values? Is it aleatoric uncertainty or epistemic? Epistemic, yeah. It's clearly epistemic uncertainty. And the answer is navy. I always forget to wear pink socks and say, haha, you're all wrong. Because obviously if I know I'm going to ask the question, I can fool you. But actually, they're good guesses. Black, navy, grey. If I was Italian, you should just look at the colour of my shirt and then say it's the same colour as your shirt because you're stylish and Italian and you wear the same colour socks as you wear shirts. But I'm not, so you have to just guess he's English. He'd just wear black or navy or grey. Okay, so that's epistemic uncertainty. Now here's an interesting one. I like this example. What happens if I take a leaf of paper like this, I have to remember to put back in, and I drop it to the ground? Where's it going to land? Is that aleatoric or epistemic uncertainty? Aleatoric, yeah. So I think you have a natural feeling for these different types of uncertainty. That's an aleatoric uncertainty. But the reason why I personally think that this distinction is a little bit odd is because you can start blurring it, right? So if I play billiards and I shoot a billiard ball and I hit one billiard into the other, my uncertainty about where things are going to go, is it aleatoric or epistemic? Yeah. I mean, I think it's aleatoric. What if I tell you actually the launch speed and direction that which I fire the billiard ball with? Or if I know it's possible to know that, if I know it's possible to observe that somehow. So there's a recording of the system, and then actually it's looking at the way the billiard ball's being fired initially, and I just am choosing not to look at it. Is the uncertainty about where the second billiard ball's going to go aleatoric, not the first? So the first one we're going to sort of there's possible information we could see about what my launch speed was, the initial conditions. So is that epistemic or aleatoric uncertainty? Yeah, I don't know. I mean, it's hard, isn't it? Because actually what starts happening, so billiard balls, I choose that example purposefully because billiard balls, if you get a large system of billiard balls, you've got a chaotic system. So chaotic systems are systems whereby knowing that launch speed of the billiard ball has to be known extremely precisely in direction in order to know the final outcome of the system. So if you run this system for a while, so chaos is the case where small changes in initial conditions can lead to very, very large changes in the final condition, right? That's what chaos means. And so epistemic uncertainty says, well, in principle, you could know this launch speed, but actually this sort of aleatoric effect we see, this sort of dropping, what is going on when I drop this, apart from it's being collided into by billions and billions and billions of little billiard balls. So this is a sort of chaotic system somehow. I mean, I can't drop it in the same, it will change. The final condition will change. So at some point, these two start to get blurred because actually, I mean, unless you go down to quantum, there is no fundamental uncertainty in the world. But there is uncertainty and stochasticity everywhere, right? So even if in the billiard ball example, I can switch you aleatoric to epistemic, perhaps. I don't even know what the right answer is personally. But you should know the broad definitions of these two terms in terms of how people use them. Because I think you can take that billiard ball system from being something that appears epistemic slowly to being something that appears aleatoric. And I think that transition stage is unclear. But there are some natural things that you think, okay, football match. What's going on in a football match? Well, it's the same thing. When the striker kicks the ball, he doesn't know where it's going to go. You don't know where it's going to go. I mean, in the post-match analysis, they always say, oh, that's a sitter. You should always score those. But if you look at the statistics, people score them 7 out of 10 times. They don't score them that often. There's a lot of stochasticity. So we kind of think of that as aleatoric. But certainly, like, if you could just check on the internet and see the match, that would be more epistemic. But actually, the reason I focus on that is because the big philosophical split across the so-called Bayesians and frequentists, which is a really uninteresting split, I think, is about whether you're allowed to put probability distributions over things that are epistemic uncertainty. And to me it seems, well, obviously yes, but there's a massive controversy in statistics. I think if you look at the timing of the controversy and what they were trying to do at the time, it makes a lot of sense. Today, personally, I think it makes absolutely no sense. I think it's irrelevant, but I'm mentioning it because it's historic. The reason I think it happened in the past was because when people introduced statistics, this approach to uncertainty already existed, and they were trying to do something different, so they made a distinction. But that's what Bayesian means, and I don't like using the term because I don't think of it, I just think it's a natural thing to do. Gauss and Laplace did it very naturally, and I think we should too. So what do we mean by Bayesian regression? So the idea here is, why is it epistemic? And I think this is also a little bit odd, because in principle, if we really believe in the model, like somehow C represents the speed at which, the pace at which, people were doing marathons in the year 0. Yeah, so Joseph would have done a marathon, or Mary or something. And so the idea is that that's an actual speed, and therefore you can't put a distribution over it. I don't accept that at all. I think that it's uncertain what that speed would have been. I think in this case it's clear you could put a distribution over it. And that's what we do. We sort of say, so before we see anything, before we see any data, we say that we believe that the offset will be drawn from probability distribution. And that's the form that we'll take in this case. Now what we then do is we combine that probability distribution, which is known as a prior distribution, with a likelihood, P of y given C, which is known, so that's the thing we've been using before, right? So here I've just focused on C, we've been using P of y given W. So this is what we've been maximizing with respect to. So we've used the likelihood a lot, but what we're going to do now is say, combine this likelihood with the prior, ignore that bit for the moment, and then we're going to use that, well, let's just write that on the board. Remember in the first lecture we looked at the sum and product rules of probability. So this is known as Bayes' rule, but it's not even a rule. It's really dumb. I mean, it's just P of C, P of Y, P of... Actually, I prefer to write them like this. It doesn't matter the order I write them in, but I prefer to write them like this. P of Y given C, P of C. That's the product rule. What's that equal to? Yeah, P of C given Y, P of Y. Why is that the case? Because that's P of Y comma C, and that's P of Y comma C. Yeah? That's called the product rule. Apparently, if you know the product rule and you have the ability to divide, that's Bayes' rule. It's not complicated. It's trivial. It shouldn't even be called a rule. It's just proper application of one law of probability. But philosophically what it does is very interesting. If you read what this says, the probability of the offset given your data. So you start with some belief about what this offset is, and then you combine it with the likelihood, and then you get an updated belief of what that offset is given the data. It's very, very elegant. It's like the fundamental thing underpinning the robot cars. Robot car has a belief about where it is, how fast it's going, so on and so forth. It scans a cyclist and it updates itself. It gets some data or it gets some information about where it is. It's all being driven by this. Sometimes in that case it's known as Bayes filtering, which is also an ugly name. It's how we got to the moon using something called a Kalman filter, which can be interpreted as in this way. So you start with some belief, you observe something, and you gain an updated belief. Now that is done using actually fundamentally a very complicated operation known as multiplication. We'll ignore the normalization, but look at that on the top there. That's the important bit. Because these two bits here, this is a function of C. This is a probability distribution over C, which also means it's a function. It's a special type of function of C. But this is a function of C. It's not a probability distribution over C. And so this is saying that this is a function of C is the result of multiplying two other functions of C together. And then when you see that, this bottom bit here, what that's responsible for is making sure that function normalizes. Because if I multiply two functions together, I won't get a probability distribution. So the role of this thing here says, please normalize yourself as well. It's a constant in C, right? So it's just make sure the integral of this top function is 1. Okay, so what does that look like pictorially? Well, this is our prior distribution over C. So it's saying we believe it's 0 with some sort of standard deviation of, well, I can't remember. It looks quite small. Looks smaller than I had it before. Let's say half or something, maybe 0.25. Now, this is the likelihood. This is the likelihood we've been using before, that y is centered around mx plus c with variance sigma squared. Now we can plot this as a function of c. Every other time you've seen it, I've plotted it as a function of y. Here I'm plotting it as a function of c. It just so happens that in the Gaussian, and this is specific to this parameter, in the Gaussian, right, y minus mx minus c squared, y and c are appearing in here. You could flip this around and you'd get the same thing. So it doesn't matter whether I plot it as a function of c or y, it looks the same. But that's rare, that's specific to the Gaussian. So other things would not look like a probability distribution when you plot them. They're just functions. So it does look like a probability distribution, but it's coincidence. It's just it's an odd thing. But this is the likelihood plotted as a function of c, the likelihood function. And what we're going to do is multiply them together. So the multiplication is going to flatten out in this region and flatten out in this little region here, because what you're trying to find is where the prior and the likelihood function agree. So the likelihood function says, look, the parameter, what we would normally do is just set the parameter here. Maximum likelihood says go to the maximum of the likelihood function. But what we're going to do in this case is we're going to have an argument between the prior and the likelihood, and then we'll see what comes out. So if you multiply those two functions together, you get this. It's rather a complicated expression of these things, but you get a new function. Well, actually, you get a new distribution if you normalize it correctly. But initially, just multiplying them together would actually have a function that's only about that high, because here is 1, 1 and 1. So 1 times 1 is 1. So the initial function would be there, and what I've actually shown is the normalized function. And it just happens, in this case, very specific to Gaussians, it's another property of Gaussians that we like, is that the product of these two things also has another Gaussian form. And that's because, I think it's probably on the next slide, so before I write it on the board, let's check the next slide. Because of this, Gaussians have this exponentiated quadratic form, e to the a squared times e to the b squared. But that is just e to the a squared plus b squared. So if you multiply two Gaussians together, you've got one exponentiated quadratic times another exponentiated quadratic, and your result is an exponentiated quadratic. This is kind of rare, right? You know, not many functions, when you multiply them together, stay within the same class of functions. In fact, it's super rare. So it's one of the reasons why Gaussians have lots of nice properties. So the product of the prior and the likelihood gives you a posterior which is also Gaussian. Now the challenge for Bayesian inference in many, many cases is you can't actually compute the posterior. So if we just have in general, we might talk about parameters as theta. Okay, so normally multiplying these two together does not lead to something that's in the same family as this. In fact, there's a certain set of distributions where this is the posterior, it's called, this is the prior, and this is the likelihood. The cases, so it's quite often the case that you can get, not quite often, it's sometimes the case that you can have the posterior in the same form as your prior. So you can find a function that combines with your prior and gives you the posterior in the same functional class. Those are called conjugate pairs. So conjugate, if you've got a likelihood that's conjugate to your prior, then your posterior is in the same form. It's called conjugacy. We're not going to study that much more. I'm just sort of mentioning it in passing. If the likelihood is Gaussian, and then that is conjugate to a Gaussian prior because you get a Gaussian posterior. What's very rare is to have a likelihood that's Gaussian combining with a, well, to have a likelihood of one class combining with a prior of another class leading to something in the first class. That's kind of specific to Gaussians. Now, you can't necessarily do this in general. So you can't invent any prior and any likelihood and automatically compute the posterior. Why not? I can multiply any two functions together, right? So I can always do the multiplication. That's simple. So what's difficult about this? Done? To get, sorry? Oh, well, finding the prior, well, no, you can just, I mean, I'm assuming I'm defining a prior. In some sense, the whole, you're right, like all of machine learning is difficult. You've got to define a likelihood and a prior. That's actually probably the hardest thing. But let's assume we've got past that. Someone's given us a likelihood and a prior. What difficulty will we face given the likelihood and the prior in computing the posterior? It's not multiplying two things together. That's easy. If I've got, someone's given me a likelihood and a prior, to get the posterior, what else do I need? Normalize, yeah. P of y. So what's P of y? I need to compute P of y. And in general, computing P of y involves the sum rule. So marginalization. If the number of parameters is large, this is a high-dimensional integral. And high-dimensional integrals are like the bane of all maths or something. So when they invented, so there's algorithms called the Metropolis Algorithm. And as far as we know, or as far as we can work out, the Metropolis Algorithm, which is a stochastic approach for integrating high-dimensional things, was invented for developing the atomic bomb, because they needed high-dimensional integrals for that. It's used actually in Bayesian inference quite a lot now. And in that case, they built like the earliest computers to compute that sort of thing. So high-dimensional integrals become the main numerical sort of bane of Bayesian inference. We're not going to look at them, right? Because we've chosen a case where this is trivial, actually. It's trivial because in our case, this joint distribution is Gaussian, and marginalizing on a Gaussian is trivial. So it just all works out. But please don't believe for a minute that what we're going to do, which is very easy now, is easy in general. It's actually a sort of real big subject for open research. Okay, so this is what it looks like mathematically. And what we're going to do, all the proofs we're doing are just end up completing this square. But our proof now is going to be slightly special because what we do is we multiply the two together like this. So I've included the extra conditioning here. Notice there's no conditioning on C on the bottom, whereas there's a conditioning on C on the top. Now, normally you would expect to have to do that integral over C, which is tractable. But in this case, we don't do it. What we do is we use this trick. This is the standard trick for any conjugate likelihood prior pairing, that you can ignore the integral. Why? Because what you do is you write this down, and then you recognize the form of this as a probability distribution in C. So knowing a probability distribution is the same as knowing an integral. If you know the form of a probability distribution, if I know the Gaussian density has the form exp of minus y minus mu squared over sigma squared, and then what do I have to put over at the front? Square root of 2 pi sigma squared. Perfect. So you know an integral. You know an integral because you know this integrates to 1, which means that you know the integral of that is equal to square root of 2 pi sigma squared. Yeah? So if you know a probability distribution, you know an indefinite integral. The objective underneath here, this is an indefinite integral over C. So what you're doing, the trick we use to do the Bayesian inference we're going to do is you basically write, you ignore the fact that this is a constant, that this has a normalizing constant. That normalizing constant is not dependent on C in this case, it would be, right? You're playing with C here. That normalizing constant does not depend on C. You write this product down and then you recognize, aha, that has the form of a Gaussian, and I know the normalization for a Gaussian. I know the integral. So effectively, you drop that step. You never actually have to do that nasty integration. So now how does that look like? I'm not going to spend detailed time going through this because I'd rather spend more time on the multivariate case. But the univariate case is here for completeness. This is the thing we've been doing in maximum likelihood, right? But now what we do is we look at the log of the posterior. So now we've got the log of the likelihood plus the log of the prior. The log of the prior is 0 mean, so it's just c squared with alpha as the variance. So we're just getting an additional term on the right-hand side here. Now when I complete the square, I get an additional term inside on the c squared. So remember what you've been doing before. When you were doing the maximum likelihood, you would write this down and then you would optimize, you would differentiate with respect to c. We're not going to do that this time. But the first step is the same. I collect all the terms up, but I get this additional term in c squared, which is coming from here. So when I multiply out here, I get c squared here, multiplied by 1 over sigma squared, and it appears n times, so an n over 2 sigma squared. But then I also get this term here. Now we complete that square. Completing the square in this case, we're going to do it in the matrix case. Probably in the lab, I'll do it on the board. But completing this square is just rewriting this thing in the form of c minus mu squared, 1 over 2 tau squared of c minus mu squared plus constant. Why are we writing it in that form? Because this is the log of the posterior. And we're trying to get it into a form that looks like a Gaussian. So this is a form that looks like a Gaussian, and the mean of this Gaussian is mu, and the variance of this Gaussian is tau squared. And everything else that is constant here, it's constant in C. We're saying anything that's constant in C, we can just put outside, because it just falls into the normalization. What you want to try and get is you want to get this this term set up such that you see something that when you exponentiate looks like a Gaussian. And that's the form. Now, there's a bit of jiggery poking around, but it turns out that in order to do this, for completion of this square to work, you have to identify that tau squared must equal this, which is just 1 over half of that, 1 over twice that. And mu is equal to this. So we'll do that more slowly in the lab. Because what I want to get onto with the slides here is actually what the result of that is in the multivariate case. Because I don't really care, I did this before, I do the sort of univariate case. I kind of have it there to reassure you that there's something out there. But actually it's multivariate where it gets interesting. Multivariate is really the one we care about. You can do Bayesian inference in one dimension, but it's not so interesting. So what we want to do is the same operation in multivariate. But in order to do that, we first have to introduce somehow I've got that in twice. Whoops. We have to introduce a multidimensional Gaussian. So what we've looked at so far is Gaussian densities over height and Gaussian densities over weight. If we assume that we want a distribution over height and weight, we talked about this before, we could multiply them together. So here's an example of what multivariate looks like. So this could be a prior distribution over M, and this could be a prior distribution over C. Our joint distribution over M and C would be the product of the two. And the product of the two looks like this. It has a sort of axis-aligned oval contour. And you can think about what this means in terms of sampling. What it means in terms of sampling is I can sample from the height, I can sample from the weight, and I can plot one against the other. And that's what we're saying for the joint distribution. So I can do that for all points. But this isn't very interesting because I can just sample from height and weight independently. What we want to deal with for multivariate Gaussians is this sort of case. A bit like, remember when we looked at, and this is going to relate, this totally relates. Remember when we did optimization, coordinate ascent-wise or stochastic gradient ascent-wise? We saw surfaces which were correlated like this. Well, they were error surfaces, so they were quadratic error surfaces. This isn't a quadratic error surface, this is a Gaussian bump, but I'm using one contour to draw it. On the error surfaces, I used multiple contours. So this is one contour at one standard deviation of the Gaussian bump. So if you want to picture what this looks like, think of a hill. Think of the Ayers Rock or Uluru, or however it's called. So you're looking at a hill on a plane, like a volcano sticking out. Now the interesting thing about the way that we've drawn this is a correlated hill. If you look at it from that direction or that direction, you see exactly the same thing you saw before. Yeah? Because from your projection, if I'm looking down here, I just see the edges of the hill are there and there, and I don't get the perspective, in this imagined example. So I just see a width of a Gaussian that's like that. If I'm looking from down here, I see a width of a Gaussian that's like that. Those are the marginal probabilities. Those are these probabilities. That's what I see. But they may be the marginal probabilities, but in practice, and actually these samples aren't great, what typically should happen is when samples come out is that they tend to be correlated. So any high sample, and you don't really see enough data to see it here, but any high sample, so actually you wouldn't know that they're correlated. They are, I know because I wrote the code. Any high sample is more likely to be high. A high sample for H is more likely to be high for W. And similar with any low sample. So actually this is very different. You can't independently sample from these two things. There's actually, if you know the sample is here, in this dimension, the conditional distribution of W is actually now a Gaussian up here. If you know the sample's down here, it's now a Gaussian down there. So your distribution, I mean, it's because it's a joint distribution. If we look at the probability of weight and height, it's no longer writable as this. That's independence. In general, of course, we need the product rule, W given H. So if you wanted to do a joint sample, you could sample from H, but then you would have to use H and sample W given H. You have to know what H is if they're not independent. If they're independent, you can do the two. But what I like to look at for Gaussians is what that object actually looks like. And that object to me just looks like a rotated independent Gaussian. So if this sausage was actually rotated, if we sort of turned the axes around like this, we could find a direction in which these two things are actually independent. And this is actually an unusual aspect for Gaussian densities. It's not a general thing, but it does work for Gaussians, and I like it as a way of introducing them so you get an understanding of what the Gaussian structure is. So let's take, mathematically, what I've written down here is the product of a Gaussian over weight and height. That's the normalizer, just multiplied together. And here's the contents of the exponential. Now I can rewrite that object in a vector form. So rather than what you've seen here, this rather ugly thing here is W minus mu1 divided by sigma 1 squared, H minus mu2 divided by sigma 2 squared. But here, I'm saying W minus mu1 multiplied by this matrix here, which is 0 at the bottom, but sigma 1 squared at the top, times W minus mu1 for that top one. So I get that element out, and so on and so forth. I'm writing it in matrix form, but with a diagonal matrix. So it's the same as that, basically. So because it's the same as that, what I can do is say, okay, that's a vector, and that's a vector, and that's a diagonal matrix. So I'm denoting the diagonal matrix D. And actually, I can replace this product of elements here with the determinant. The determinant of a diagonal matrix is the product of its elements. So what I'm showing you here is the determinant of D. So now I've got this thing in something that looks like a matrix vector form, but it's still axis aligned. And what we want to do is rotate this whole space. So what I said here is if I can take an axis aligned Gaussian and I can rotate it, then I'm going to get something that is sort of a full covariance Gaussian. And that's what I'm going to do mathematically now. So I'm introducing R, which is a rotation matrix. So R rotation matrices have the form R transpose R is equal to I, or R transpose is equal to I, the identity matrix. They just take any axis like that. If that's an axis, it can be written as a matrix, and they'll rotate it around. You'll see them in like 3D graphics. You see them popping up everywhere. It could also have a permutation in it as well, but let's just assume it's a rotation matrix here. So what we're doing to rotate the system, we rotate all the y's and we rotate all the mu's. But what that allows us to do is actually pull that R, because this whole object is transposed, I can pull that R out here and put it by D. So on both sides I can do that, which gives me this object. This is what we call the covariance matrix. RD minus 1R is actually RD minus 1R transpose is the covariance. Now what does that mean? Let's take those original standard deviations, sigma W, sigma H. If I rotate these standard deviations, so that's what we're calling D, that would be D to the half, because our D was the form of sigma W squared, sigma H squared, 0, 0. If I rotate this object, I get a new set of axes like that. Yeah? And what the covariance matrix is not that object rotated, it's that object rotated times the transpose of that. Yeah? So it's R D to the half, D to the half, sorry, minus half, R transpose. So this, all this object is doing is it's taking the data, it's first of all rotating it back to two aligned axes, and then it's scaling it. So you can think of the way the multivariate Gaussian works, in some sense. I mean, it's not, it doesn't work in any way, it's just maths. But one way you can think of what it's doing is it's taking data in, it's saying, oh, all you data, you're all correlated, rotate yourselves back to these directions where you're non-correlated, and then scale yourselves back in this way, and actually once you've done all that, you're back to a standard circular Gaussian. The rotation and the scaling, so you're sort of like, like that. That's your starting point, and then the model says, well, actually, the covariance will have axes like that, and it will say basically rotate yourself back down to that. Well, let's put it up that way, which means rotate first of all, so turn it into with those axes, and then now scale yourself into something of that form. Yeah? And then once you've applied that, downscale yourself, once you've applied that operation, then it's just e to the power of that thing, right? Note on the left-hand side, the determinant of this object, the determinant of D is actually equal to the determinant of C. So you end up with this determinant term at the front as well. So that's how I think of physically of the Gaussian. I mean, you can read a lot more about the mass of the Gaussian, and I urge you to do that in your own time. What we're going to do in the lab class, at the start of the lab class, is I'm going to apply that to what it means to do Bayesian inference in multivariate spaces. But just to give you an idea of the sort of results you can get, this is the polynomial data again. So let's, actually no, before we go through that, let's stop and, I know I went through that quite quickly because it's sort of, part of it's review material, but it's review of stuff that you won't have seen in a while. But the main thing I want to get across is there's the physical understanding of, I mean, it's not a physical object, right? But personally, I always work, mentally, I have to have an intuition about how something's working so I can understand it. And that's, I wanted to get that intuition across. So let's just take questions for the last 5 minutes, because I can also show the Bayesian polynomial results in class on what I've said about the multivariate Gaussian and how it comes about. Probably all too much in one go. People know about determinants is an interesting, so does people want me to say a little bit about the determinant side? Because determinants is something that also aren't that often talked about. So a determinant of a matrix, well, I kind of think that the determinant of, for me, the determinant is always, for the Gaussian, the determinant plays a very important role. What is the determinant? What's the determinant doing? We talked about it earlier. What's the role of this bit outside? It ensures what? It's not a function of y, but what does it ensure? Someone mentioned it before when I said what's the integral of the univariate Gaussian? Yeah? It's doing what? Normalizing, yeah. Yeah, the determinant's the normalizer. So in the univariate Gaussian case, the normalizer, unsurprisingly, has the form of being that length. Yeah? So it's sigma squared. So it's sigma. It's not sigma squared, is it? It's sigma. In the univariate Gaussian, the normalizer is, it's got this funny 2 pi, and it's square root of sigma squared, so it's sigma. It's something proportional to sigma. That's what the integral equals. Yeah, that's what that integral equals. It's sigma. Not unsurprisingly, that's associated with the width of the Gaussian. Okay? Now, determinant of these symmetric matrices can be thought of in this way. We don't normally call them sigma, we normally call them lambda. Lambda 1 and lambda 2 in 2 dimensions. These are the eigenvalues of a matrix. They're also a set of principal axes. And the determinant of, let's say that this is a covariance based on a Gaussian with these principal axes. The determinant of the associated matrix, which is lambda 1, lambda 2. So why do I make that into a matrix? That's vector lambda 1, which is that vector. This point is vector lambda 2. Sorry, is this vector here. So these two bases can be written like this. They're an orthonormal basis. The determinant of this is actually this area, because the determinant of this object is equal to lambda 1, lambda 2. It's the product of the diagonals. Now, that determinant doesn't change if we rotate the matrix. So actually the determinant is always measuring this area. There's something that I wasn't really taught in linear algebra. I think because you tend to get taught linear algebra by people in the maths department who don't necessarily worry about what the physical meaning of something is. But the determinant of, if you took this matrix here, which is simply the original matrix lambda, let's call that capital lambda. But now we're applying a rotation. So this is now r times lambda, a rotation matrix to spin it around. But the determinant of r times lambda is the same as the determinant of lambda. That rotation doesn't affect it. It's still measuring that. In higher dimensions, you get a lambda 3, 0, 0, 0, 0, like that. And it would be measuring the size of a cube. Oh, I can't draw a cube, apparently. It's something like that, yeah? Oh, I should learn how to draw in perspective. So whereas that's lambda 3, yeah? So it measures the volume. In 4 dimensions, it's a hypervolume, actually. The determinant is always measuring the volume. But it's measuring the volume that the Gaussian is declaring. It's still its normalizer. In one dimension, it's the length of a line. In 2 dimensions, it's an area. 3 dimensions, it's a volume. In higher dimensions, it's a hypervolume. So this term here is actually giving you the volume. But that's not what appears, is it? That wasn't what appeared. Because it's actually the determinant of C, the covariance. And C is of the form, in the notation we were using before, like that. So actually, what this is saying is it's the determinant of R lambda times lambda transposed R transpose. But lambda transpose is diagonal, so that's just lambda. So it's R lambda squared R. Because in our D, we defined our D to be sigma squared, sigma squared. So actually, this object that we're looking at the determinant of is the square of these two matrices. But that doesn't matter, because the determinant of a square, the determinant of A times A, is just equal to the determinant of A squared. That's a sort of linear algebraic operation. So all we're computing here is the determinant of this object squared. But look what's outside it. In the multivariate Gaussian, on the outside of that object squared is, lo and behold, a square root. So this nasty determinant term, which is actually, it's slow to compute for very large systems, to be fair, but all the nasty determinant term is doing is computing the volume of these axes it's found, regardless of where it was in the first place. You know, maybe this, I don't know, how do we draw a, yeah, Gaussian sausage. It's just computing the volume that this object sits in. It's actually a really, really important term. It comes up in entropy, it comes up in all over the place. It sort of tells you something about how much the dispersion is and everything else like that. But you know, you'll see it all over the place. But whenever you see the determinant, just think, oh, that's just a volume. That's just the determinant of a symmetric matrix. Was positive definite symmetric matrix. It's not true in general. Determinants can mean other things. But for our cases, it's just measuring the volume of the over which this Gaussian model is sitting. So you've got something that's sort of normalizing, which is measuring the volume, and something which is basically transforming the data back to be unit variance. Who's heard of principal component analysis? Yeah? So you saw something should be ringing in your mind now, right? Because principal component analysis is the eigenvalue decomposition of the covariance matrix. Right? It's actually just finding these axes. Because you write down the covariance matrix, the way you develop the covariance matrix is actually directly from the data. You don't develop these axes and then develop, I'm just giving you that understanding of it. All this is just the eigen decomposition of the covariance matrix, and that's the principal component analysis as well. So it sort of relates to that. But I kind of think it's a really nice way to think about what the Gaussian's doing. You know, PCA and Gaussians are inextricably interlinked. Oh, we've overrun, so we better stop there. But I'll go into more detail. We'll talk more during the lab class. Stop there.